Imagine you are standing outside on a clear night. The sky is normal. The stars are where they always are. The air is still. Nothing is moving. There is no sound, no warning, no indication that anything is different about this particular moment compared to any other moment in your life. And then, somewhere in the galaxy, a star dies. Not near you, not close by any human standard, perhaps 10,000 light years away, perhaps 20. Far enough that the distance should make it irrelevant. Far enough that, under normal circumstances, it would be nothing more than a faint brightening in the sky, a footnote in an astronomy journal, something only instruments would detect. Except this star does not die quietly. In approximately 2 seconds, it releases more energy than our sun will produce across its entire 10 billion year lifespan. Not gradually, not in stages, in 2 seconds. And a narrow beam of that energy, gamma radiation, moving at the speed of light, carrying the destructive capacity of 1 billion nuclear weapons per square meter, is pointed, by the geometry of the collapse, directly at Earth. You are still standing outside. The sky still looks normal. It will look normal for exactly as long as it takes light to travel from that dying star to your eyes, and then it will not look like anything at all. You have probably never heard of a gamma-ray burst in the context of something that could end human civilization. They do not appear in most lists of existential risks. They do not generate the kind of sustained media attention that asteroid impacts or nuclear war generate. This is partially because they are rare, partially because they are distant, and partially because there is absolutely nothing we could do about one if it were aimed at us. And that particular category of threat tends to receive less attention than threats that at least permit the illusion of preparation. But let's go through what a gamma-ray burst actually is, what it actually does, and what the current data says about how close we are to the nearest one. Because the numbers are not as comfortable as the silence around this topic suggests. Gamma-ray bursts were discovered by accident. In the late 1960s, the United States military launched a series of satellites called Vela. Their purpose was to monitor Soviet nuclear tests in violation of the Partial Nuclear Test Ban Treaty. They were looking for gamma radiation, the signature of nuclear detonations. They found gamma radiation, enormous amounts of it, coming from space. The first confirmed detection was in July 1967. The data was classified for years, not because the bursts were considered a threat, but because the detection systems were classified. When the findings were finally published in 1973, the astronomy community had no framework to explain what it was looking at. Bursts of gamma radiation lasting anywhere from milliseconds to several minutes, arriving from random directions, releasing energy that, at the distances eventually calculated, exceeded anything in known astrophysics. It took until 1997, 30 years after the first detection, to confirm that gamma-ray bursts were extragalactic, coming from other galaxies, billions of light years away. The reason that confirmation took 30 years is also the reason the bursts are so dangerous. They are brief, they are bright, and they are over before most instruments can fully respond. The universe's most powerful events, and we almost miss them because they happen too fast to track in real time. There are two types. The distinction matters. Short gamma-ray bursts last less than 2 seconds. They are produced by the merger of two neutron stars, two of the objects we discussed in the previous video, spiraling into each other over millions of years until they collide. The collision releases gravitational waves, a kilonova, and a concentrated beam of gamma radiation in the axis of the merger. In 2017, the gravitational wave detector LIGO recorded the merger of two neutron stars for the first time, designated GW170817. 70 observatories around the world simultaneously detected the event across every wavelength of the electromagnetic spectrum. It was the most observed astronomical event in history. The gamma-ray burst associated with it was classified as short. It lasted approximately 2 seconds. 2 seconds. The merger of two stellar corpses, each containing the mass of a sun, compressed into 20 kilometers, spiraling together for 100 million years, releasing, in the moment of collision, a beam of radiation detectable across 130 million light-years. 2 seconds. Long gamma-ray bursts last more than 2 seconds, sometimes several minutes. They are produced by the collapse of a massive star directly into a black hole. The collapsing core generates a jet of material moving at close to the speed of light. When that jet punches through the dying star's outer layers and escapes into space, it produces a burst of gamma radiation that, in the right orientation, is the brightest thing in the observable universe at that moment. Brighter than entire galaxies. For minutes. Now let's talk about what that beam does when it arrives. Gamma radiation at the intensities produced by a burst is not like the radiation from a nuclear reactor or a medical X-ray. It is not a dose that accumulates over time. It is an event. The beam travels at the speed of light. It arrives without warning, because the warning would also travel at the speed of light, arriving at the same moment as the radiation itself. There is no early detection. There is no preparation window. There is arrival, and there is aftermath. What the aftermath looks like depends on distance. At a range of several hundred light-years, a gamma-ray burst aimed at Earth would be an extinction event. Not gradually. The initial radiation pulse would ionize the upper atmosphere within seconds, stripping electrons from nitrogen and oxygen molecules, producing nitric oxide in quantities sufficient to destroy the ozone layer globally within days to weeks. The ozone layer does not regenerate quickly. Its loss would expose the surface to ultraviolet radiation from our own sun, radiation that, without atmospheric filtering, is lethal to most surface life, most shallow water marine life, most of the photosynthetic organisms at the base of the food chain. A 2004 paper in the Astrophysical Journal by Malott and Thomas modeled the gamma-ray burst at a distance of 6,000 light-years, well within our galaxy, and concluded it would destroy approximately half of Earth's ozone layer in 10 seconds, with full recovery taking years to decades. The ultraviolet flux reaching the surface in the years following would be sufficient to cause mass extinction at the level of the end Ordovician event, the second largest extinction in Earth's history, which eliminated approximately 85% of all species. The paper noted that the geometry of the burst matters enormously. A burst aimed directly at Earth is catastrophic. A burst at the same distance but aimed elsewhere is undetectable without instruments. We have no way of knowing in advance which type we are facing. The beam moves at the speed of light. So does the information about its direction. Here is the number that reframes everything above. At any given moment, approximately 1 gamma-ray burst is detected somewhere in the observable universe every day. 1 per day across 2 trillion galaxies. Most of them are billions of light years away. Most are in galaxies with no relation to ours. Most are pointed in directions that make Earth irrelevant. But the galaxy is not static. Stars are being born. Massive stars, the ones that produce long gamma-ray bursts when they die, have lifespans of only a few million years. They form, they burn, they collapse, all within a time frame that is short by astronomical standards and long by human ones. There are an estimated 100 million massive stars in the Milky Way at various stages of their life cycle. Each one is a potential gamma-ray burst source. Each one will, at the end of its life, collapse, and some fraction of those collapses will produce jets, and some fraction of those jets will be oriented toward Earth. The current best estimate for a gamma-ray burst within lethal range of Earth, within several thousand light-years, with a beam oriented toward us, is roughly once per billion years. Once per billion years. Earth is 4.5 billion years old. Statistically, it has happened before. There is a hypothesis first seriously proposed in 2014 by Perron and Jimenez that a gamma-ray burst may have caused the end Ordovician mass extinction 440 million years ago. The end Ordovician killed 85% of marine species. Its cause has been debated for decades. The leading candidate has been glaciation, a rapid ice age triggered by the breakup of the supercontinent Gondwana. But the glaciation model has gaps. The pattern of species loss does not perfectly fit a cold temperature die-off. Marine species that should have been protected by deep water show the same extinction rates as surface species. The gamma-ray burst model fits several anomalies in the fossil record that the glaciation model does not. The pattern of ozone depletion, followed by UV radiation damage, followed by food chain collapse, produces a specific signature in which species survive and which do not. That signature, Perron and Jimenez argued, is present in the Ordovician record. It has not been confirmed. It remains a hypothesis, but it has not been ruled out. If it is correct, then you are the descendant of the organisms that survived a gamma-ray burst. The life that made it through the ozone collapse, the UV exposure, the food chain disruption, the years of reduced photosynthesis. The filter was lethal to 85% of what existed. You are in the 15%. You are still standing outside. The sky is still normal. The stars are still where they always are. Somewhere in the galaxy, right now, massive stars are in the final stages of their lives. Some of them are oriented toward Earth. Some of them will collapse within the next 1,000,000 years, a blink by stellar standards. Some fraction of those collapses will produce jets. Some fraction of those jets will point in our direction. We will not see it coming. The physics does not permit advance warning. The beam and the information about the beam arrive simultaneously, at the speed of light. What we do know is this. The event will last between 2 seconds and several minutes. The ozone layer will begin to break down within the first 10 seconds of arrival. The UV exposure will begin within days. The ecological cascade will take years to play out. And somewhere, in the fossil record that accumulates over the next several million years, the organisms that survive will leave a signature. A sudden gap in the record. A change in which species persist, a layer of rock that marks a before and an after. The organisms that come after will eventually develop science. They will eventually look at that layer and wonder what caused it. They will propose hypotheses. Some of them will be wrong. One of them, if they are methodical enough and lucky enough, will eventually point at the sky and describe what happened. The way Perron and Jimenez pointed at the Ordovician. They will not be able to prove it, but they will not be able to rule it out. Here is your question. The last confirmed gamma-ray burst within our galaxy was detected in 2004 from a magnetar designated SGR 1806-20 at a distance of approximately 50,000 light-years. It was not aimed directly at Earth. It still caused measurable ionization of the upper atmosphere from that distance. 50,000 light-years, measurable ionization, not aimed at us. If you could know, with certainty, whether a gamma-ray burst capable of causing a mass extinction event will occur within lethal range of Earth in the next 1,000,000 years, would you want to know? Drop your answer below and tell me why. Next video, the force that is currently pulling the universe apart faster than light, and what the math says happens at the end of that process to everything that currently exists, including the atoms you are made of. See you there.